Howdy, folks. Let's continue our discussion of oscillations and waves, and a quick recap here on, on simple harmonic oscillators. There are two primary systems, but more than two, but two primary systems that are called that we talk about as simple harmonic oscillators that undergo what's called simple harmonic motion. And here's what's common about them. All right, here's a pendulum. A pendulum has an equilibrium position, right? Where this pendulum bob sits here, and the only force acting on it is mg. Well, sorry, there are two forces acting on it, T and mg, tension and weight. And then here's this other system. It's a mass on a spring, and here's an equilibrium position. And at this case, or at that location, at least in this direction, there are no forces acting on this thing because this is at an equilibrium position. All right, the spring is at the spring's at its natural length, not extended or compressed, does not exert any force. All right. Now, this pendulum system can be displaced this way. There's a delta theta or a theta. The mass on a spring can be displaced, let's say, this way. Here's a delta x, so we have the object now over here. And when that happens, well, for the mass on for the pendulum, there is now, well, this force mg has a component that way. I'll call that mg perp. All right, and mg perp creates a linear restoring torque. I'm not saying mg is a torque, mg is a force, but it creates a linear restoring torque. As long as, blah, 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 small angle oscillations, you can't drag this thing up to the ceiling. You have to make theta, quote, sort of small, around 20 degrees for a maximum or so. But if you do that, mg creates a linear restoring torque, which means that the torque exerted by the force is proportional to, but in the opposite direction of, right? Proportional to, but in the opposite direction of the displacement. All right, over here, what happens is the spring force, because now there's a spring force acting on this object, exerts a linear restoring force. All right, in this case, the spring force quite literally is a force. All right, and that says, both of these things say that the more an object is displaced, the more force or torque is exerted on it back toward equilibrium. Well, and the result of that, in this case, the result of that net torque is an angular acceleration back toward equilibrium. In the case of the mass on a spring, there's a center of mass translational acceleration back toward equilibrium. And what happens is both of these accelerations, whether they're angular or translational, look like this. When there's a big positive displacement, there's a big negative acceleration. When there's a big negative displacement, there's a big positive acceleration, and so on. So what you get for acceleration, whether it's angular or translational, is something that looks like that. And, well, I mean, we have ways of expressing the size of the acceleration in both cases. And it says that if the torque is proportional to displacement, or if the force is proportional to displacement, that means acceleration is proportional to displacement, but in the opposite direction. And that means that accurately, the only way to represent this kind of motion is with sine and cosine graphs. The sine/cosine graph. So this I should have written up here. This is either theta as a function of time or linear position as a function of time. These are both time. All right, there's only one kind of function where if you look at, well, let's see, this is position. The rate of change is velocity. And the rate of change of velocity is acceleration. There's only one kind of function in the universe where if you look at you know, the rate of change of the first function, of the position function, you're going to get a function that looks just like that, but in the opposite direction. So this says that the position functions have to be described mathematically as sine or cosine functions. Okay, so these simple harmonic oscillators are mathematically modeled like waves. A pendulum isn't a wave, and a mass in a spring isn't a wave, but mathematically they can be modeled that way. However, some phenomena are actually waves. And what they do is there is something somewhere that oscillates back and forth, and that oscillation, well, is transferred. The energy associated with that oscillation is transferred through space and or time, and quite literally, or material. And that's what a wave really is. All right. So for example, there are a couple different main, what's the word I'm looking for? Types is a crap word. Categories, thank you, of waves. And so of those, primarily, we're going to talk about light versus sound. All right. Now, when we talk about light, light's a part of a big group of waves called the electromagnetic waves. I'll write it out. Light is one. When I say light, I really mean, you know, I'm referring to visible light. So this is part of the electromagnetic waves, and that includes things like infrared and ultraviolet and microwaves and X-rays and radio waves and gamma rays and all that sort of stuff. All right, and then for those kinds of waves, what's actually happening is somewhere a charge is oscillating back and forth. All right, and the oscillation of a charge creates electric and magnetic waves, or fields, I should say, fields. And those fields change size and direction, and that change is propagated through space so it can be detected in other places. All right, sound is one of what's called the mechanical waves. Yep, there's an E. Mechanical waves. Where mechanical waves, well, some physical object is oscillating somewhere, and that oscillation is transferred through or by other physical objects. So the big deal with sound and mechanical waves is that some physical matter oscillates, as opposed to, for an electromagnetic wave, a charge oscillates. All right, but the oscillation of charge, like we said, makes fields, electric and magnetic fields, and those fields don't need any stuff to travel through. But for sound and other mechanical waves, there is a requirement of physical matter to oscillate, and that means that, well, mechanical waves have to travel through stuff. They can't travel through nothingness. Light and electromagnetic waves can travel through nothingness, the nothingness of the vacuum of space. All right, mechanical waves have to travel through stuff. But, so there are, you know, certainly differences in types of waves, but waves all do the same thing. And what they do is they transfer energy from place to place. That's a star, without transferring matter. Without stuff moving from place to place. Okay? So when you are hearing me talk, it's because there's a speaker diaphragm, a little round disc in a speaker that's vibrating back and forth. And what that does is bumps into air particles really close to the speaker diaphragm. And that first air particle right next to the speaker diaphragm oscillates back and forth. That air particle doesn't travel from the speaker into your ear. What each air particle does is oscillates and bumps into the one next to it. And the bumping of the one next to it then makes that one bump into the one next to it, and that bumping is propagated through space, through air, okay, but through physical space. And therefore, the oscillation, that quite literally the movement, the kinetic energy, right, the movement of a speaker diaphragm, that kinetic energy is transferred to the movement of your eardrum. So kinetic energy is transferred without transferring air particles from place to place. Air particles oscillate about an equilibrium position. Okay? And so waves can look a couple of ways. Here's one way a wave can look. Thanks to the wonderful folks at FET at Colorado Boulder, this is a simulation of a wave traveling on a string. All right, so restart, stop. I mean, how do I stop? Manual, sure. So what we can do is there can be some oscillation of this wrench, or really like the first, quote, the first particle. And what happens is, you know, the wrench doesn't have to move from place to place, but the energy associated with the wrench's movement is transferred from place to place. Okay, and when we do this, right, we can see that this energy is transferred, this energy of the kinetic energy of this oscillating, you know, turning object that makes a thing go up and down, that energy is transferred. Well, to look at slow motion, look at the, so this particle here, where before it didn't have any kinetic energy, the kinetic energy of this oscillator is transferred to each and every one of these particles. Okay, what's neat to look at, and the color coding really helps here, is we notice that, wow, look at this, you know, look at this peak move, move, move down the line. But what's happening to any single particle is the single particle isn't moving down the line. The single particle stays, you know, quote, where it is, but it oscillates this way as the wave travels this way. So that characterizes or qualifies this kind of wave as what's called a transverse wave. All right, so these kinds of waves on the left are called transverse. Where the wave propagation, or the direction of wave propagation is that way, but these objects each oscillate up and down. Perpendicular. And in this box, so hint, the wave moves, or in the word I'm looking for here, the vocab word here is propagates. This wave propagates to the right, but the parts of the wave oscillate perpendicular to direction of propagation. All right, there are lots of kinds of waves that do that. Now there are other kinds of waves that are called longitudinal, where parts of the wave oscillate. It's hard to see this, but well, there's a nice little animation of this. There we go. I should give credit here. ISVR. Who's the ISVR folks? Come on. That's oh, University of Southampton. Thank you very much, University of Southampton. Look at this model of a longitudinal wave. Here's, look, this red oscillator on the end is like a speaker diaphragm. All right, or it's like a vocal cord, or it's like a tuning fork, or it's like a something that is something that's making sound happen. And what it's doing is oscillating back and forth, and what that does is push air particles together. I don't know why it's changing color, don't worry about that. Push air particles together and then spread them apart, and then push them together and then spread them apart. And that compressed part can propagate through space. This is the compressed part here. See right above the mouse? That's an area of what we call compression. That compression peak can travel, well, does propagate through this medium. Now, they do an awesome job here. If you look at a single particle, right, I've identified those red dots for you. Those red dots don't travel down the line, quote. What they do is they oscillate back and forth. All right, so this, again, is the transfer of, well, you could call it a couple different things, but there are, large amounts of things and small amounts of things at different places and times, right? But each of these parts doesn't travel along with the wave, right? Each of these parts, as the wave propagates to the right, as this wave propagates this way, one of these particles oscillates back and forth like that. That's called a longitudinal wave. The direction of oscillation is along the direction of motion. Now, this is a super pain in the butt to draw. You probably won't draw it that way. But what you can do is still represent this like this. All right, so what we have, look, this is like saying, well, there's a lot of something. There's a less than normal amount of something. Not a negative amount of something, but if this is like the equilibrium amount, well, there's more than equilibrium, here's less. Here's more, here's less, here's more. Okay, so what is that amount? What's more than normal? Well, maybe it's particle density, right? Particles per unit volume. For us, it's probably pressure varies as a function of position. Or maybe it varies as a function of time. Both of those things will be true. Okay, so each particle here oscillates parallel to the direction that the wave propagates. This wave also propagates. Parallel, I'll say, to direction of propagation. Okay, so you have to be able to talk about categories of waves. One is, electromagnetic, or really we can call these also non-mechanical. You have to discern between non-mechanical waves and mechanical waves, because the question is, does physical matter have to oscillate or not? Right? You also have to be able to discern between transverse and longitudinal waves because of the nature of the oscillation itself. Okay? What direction do things oscillate? Along the direction of propagation or perpendicular to it? Okay, now, wave characteristics, things that we need to be able to identify about a wave. There are several. This is called A, amplitude. It's A, and its units, well, that depends, all right? That depends on what we're graphing, okay? Maybe it's quite literally position, right? Maybe it's how far something has moved upward. Maybe, like we said before, maybe it's particle density. Maybe it's air pressure. Maybe there's lots of units that could be in. Maybe it's a velocity. Oh boy. Maybe it's a acceleration. We don't know what that is. It depends on the situation. So the definition, though, is max displacement from equilibrium. Equilibrium. Sure. Controlled by depends on, well, the source oscillation. Something's oscillating back and forth, and the degree to which it oscillates back and forth is the amplitude. Okay? There's one thing. Here's another we can talk about. Now, this depends. This, peak to peak, it's either one thing or the other, and it really depends on this. Note, if this is a measure of time, then this is an amount of time from peak to peak, and we call that the period. T, definitely measured in seconds. time for one oscillation. All right, and that, it's also, right, there's also a period. Here's also a period. It doesn't have to be peak to peak. It can be any two corresponding consecutive places on a wave. Okay, if that is not a measurement of time, but if this is a measurement of position, let me do this. Let me say, what if this was measured not as time, but what if this was measured? This will make it maybe a little clearer. If this is measured in seconds, then this is a number of seconds. If this is measured in meters, then that's an amount of distance, and that distance is called wavelength. Lambda, measured in meters or some, centimeters, millimeters, kilometers, something like that. And that's distance between, how about this? Between corresponding consecutive distance between corresponding consecutive places on a wave. Now that's controlled by, well, we're going to get there in a second. What else is there? What else is there? Well, this is what we call the maximum displacement from peak to trough. Okay, I'm not going to write that on there because it's not one these are I'm leaving the primary ones on there that you're going to need to work with. There's something else that's called frequency. We call that F, and frequency is number of oscillations per unit time. All right, that for us is measured. We're going to measure our frequencies in, well, oscillations per second. Oscillations aren't really a unit. It's like saying there were 3 per second, right? I know it says 1 per second, but what I mean by that is the oscillations isn't a unit, it's a number. So frequency is measured in events per second, all right? So the per second is called hertz, or capital HZ. Now, frequency depends on source oscillation too. There is something somewhere that's oscillating back and forth, and it oscillates at some frequency based on, well, it's hard to say based on what. The thing's oscillating. How fast? That's sort of up to the thing that's oscillating. Okay? Well, period sort of depends on that, but those are sort of the same thing. And notice that their units are the inverses of each other. So we can say that period is 1 over frequency. All right, and then wavelength, I'm going to extend a bit here. Wavelength depends on frequency, controlled by frequency and something else. And that something else, I'm going to take you here. All right, we got a graph of wavelength and frequency. All right, and so I'll take you back to I'll take you back to this simulation, and note, if you will, there we are, that we can change the wavelength of this wave, watch, by changing the frequency. If we make the frequency bigger, the wavelength got smaller, distance from peak to peak got smaller. If we change the frequency to smaller, wavelength gets way bigger. This peak to, peak to peak distance just got way bigger. Okay, amplitude has nothing to do with, let me do this. Amplitude has nothing to do with wavelength. Watch, we can have a wavelength that's this long, right? And if I make this amplitude bigger, right, we get the same wavelength here as we do here. So amplitude doesn't control wavelength. The things that control wavelength, as we showed a minute ago, are frequency, right? A bigger frequency makes a smaller wavelength. But watch this. I can change the speed of the wave by changing, in this case, the tension on the string. Low tension, speed goes slowly. High tension, speed goes fast. I mean speed like this, how fast the wave travels, right? And notice that if I keep this wave speed constant, what we get is high frequency, oh boy, zero frequency, no. So low frequency, big wavelength, big long waves. High frequency, little short waves. And how this really works, these two quantities are actually related inversely. So if we were to double the frequency of this oscillation to f naught, what we get is lambda naught over 2. That's a 2. Now this is measured in hertz. And if we were to say, well, what if I had half this wavelength, sorry, this frequency, what we get is 2 lambda naught. So this graph looks like this, where lambda is related to 1 over frequency. So quite literally, if we graph lambda versus 1 over frequency, we get a straight line because those two things are proportional. And furthermore, these units are meters. These units are, well, 1 over hertz. And a hertz is a 1 over a second. So these units are actually seconds. Look, then we have the meters per second. And so the slope of this thing is in meters per second. So the slope, well, is a velocity, is the wave speed. And that says that velocity is lambda divided by 1, divided by 1 over frequency. Divided by 1 over frequency. That's the same as saying that velocity is f times lambda. Now, really accurately, the way to say this is that it's really that lambda is v over f. I thought I paused. I didn't even pause. I was talking to Miss Harrod. So really, it's that lambda is controlled by frequency and wavelength. That's what's going to go here. No, lambda is controlled by frequency and wave speed. And what we should say is that wave speed, I'll just write it in here. Wave speed v measured in meters per second. And this is how fast wave moves through space. And that's controlled by the medium through which the wave travels. So remember, the only way to change our wave speed was to change the tension on that string. Well, that's changing the nature of the medium through which the wave travels, right? In that case, the wave travels through the string, on the string, right? And if we change the nature of the string, we can change the speed at which the wave travels. Okay? All right. Now, you'll note here, I've got a different wave, right, on the right that has, well, look, very different characteristics, right? It's got a much smaller, if this is the same scale, of course, a smaller period, a smaller wavelength. It's got a smaller amplitude. All right, so different waves while they share similar characteristics in the nature of the oscillation, they're the physical characteristics, or the quantitative characteristics, I should say, periods and wavelengths and amplitudes and wave speeds might all be different. Okay. Okay. Here is a simple-ish, sort of review question. Let's look at stuff like, well, look, we're given this frequency of 25 hertz. Let's find a bunch of stuff. Let's find the amplitude. Well, they're trying to trick you here. Here's amplitude from equilibrium to peak, or from equilibrium to trough. That amplitude is 9 centimeters. All right, the wavelength, well, look, this is an amount of distance. But look, this is from peak to trough. We need from peak to peak. So this wavelength, 20 centimeters. The period. Well, we can't read period off the graph because this is not an amount of time. It's an amount of distance. But we do know the frequency. So therefore, we can say that period is 1 over frequency, 1 over 25 hertz. That's 0.04 seconds. And the speed of the wave, you're always going to do that for wave speed. Almost always. Not always. F is 25 hertz. Lambda is 20 centimeters. I'm going to turn that into 0.2 meters. So this wave speed is 500 meters, 5.0 meters per second. Fair enough? This is very much reviewy for folks in my class, but this stuff is new. Right? We have to know the difference between transverse and longitudinal waves. All right? Being able to identify these quantities from a plot of a wave's motion as a function of time or a function of distance is a must. All right, being able to relate wave speed to other stuff, really talking about the factors that control wavelength, is a must also. Okay, so that gives us a good intro into the nature of some mechanical waves. Thanks, folks.